All right. Hello, everybody. Yes, I do play competitive beach volleyball. I don't run any marathons or anything. I'm more like a grizzly. I'm good in short bursts, so I need to be able to, take a break every 25 points. All right. All right. As was mentioned, I'm going to be talking about calibrating driver behaviors in this case, on freeways. Using kind of deterministic or macro level data. A little bit of background on myself. My background's in applied mathematics, so not quite an engineering background, but this kind of fits into what we do in the simulation world with a lot of the models and things that we build out. I've been with PTV officially full time since 2014, but I was an intern before that as a VisWalk modeling specialist. So yeah, and then currently I'm a training manager, and so if you guys ever need any sort of training services, you'll be contacting me. And then conveniently, I forgot my business cards, so I included my data down here. It's really small, but if you need to get a hold of me, just come find me sometime, and I'll give you my contact information. All right, so and again, as similar to Betsy, the technical team at PTV Group, we do everything for all the software, so it's like we do training, technical support, and professional services for Vizoom, Vistro, vSim, and VisWalk. So again, kind of a jacks of all trades on our team. Okay, advance the slide. Okay, so the study I'm going to be talking about is one that I participated in with FHWA in conjunction with David Hale and the Leidos and his team and things like that. But we talked about specifically how can we calibrate driver behaviors for narrowed lane facilities, because the projects that we're looking at a lot of people are looking at these days have to do with how can we increase the capacity on our freeways without spending a lot of money to build out a lot of facilities. Maybe you're up against boundaries, or it's really expensive to purchase the extra land. So the idea is, okay, you just have to repave your shoulders, make them hard shoulders, or perhaps, reutilize that space, take them down from 12-foot down to 10-foot lanes or something like that. And then if you have 4 lanes that are 12 feet and you take it down to 10 5-foot lanes, you're able to minimize how much shoulder you're actually utilizing. But what we wanted to investigate was the impact of the driver behaviors, how people actually behave on those lanes, because there are noticeable differences in how people behave once cars start to get tighter together. So that's kind of what we were looking at. And the case study itself was on the I-270 corridor near Rockville, Maryland. All right. Unfortunately, it hasn't been published yet. So I can't really discuss all of the specific results. We finished it in 2018, or I finished my portion in early 2018, and we're just kind of waiting for all the approvals and things like that. So I'm going to be talking about it, but I can't discuss the specific findings of the actual report itself yet. I didn't get approval from FHWA for that specific stuff. But I'll talk about the process that we go through. And the important thing that I'm going to be talking about is how can you take macro level data like saturation flow rate and speed and turn them into Wiedemann parameters for your models that you're building. All right, so a quick summary was we looked at, the project started by looking at these 5 cities, different freeway corridors on these 5 cities, and we pulled speed and headway data from those. They actually used drone videos and other videos that they pulled from these different facilities to be able to pull out, and then they used some video computing software to be able to pull out the headway times and the speeds of the individual vehicles. So we got the raw data from each individual vehicle point. But you could do the same thing with induction loop detectors. The way that they set up the programs to read the video, instead of tracking vehicles across a distance, they just basically set up a gate and looked at timestamps. So virtually they spent 100 times more to just do induction loop data collection kind of stuff. But that's just my personal opinion on that. Could do the same thing if you just have induction loop detectors, is my point. All right, so continuing on with the quick study, we started with these 5 cities, and then the different cities had different facilities that we were looking at. So Seattle had 11-foot lanes. We looked at Honolulu, which had 10-foot lanes. So we were able to pull data from there. And then Dallas, San Antonio, Fort Lauderdale, and then we combined some of that data to kind of give us some aggregate values from nationwide. All right, and so we collected 10-foot, less than 10-foot, 11-foot, and 12-foot facilities. And then my job was to calibrate for VSIM. We also worked with other simulation providers, and they did their part. So since it's FHWA, it was kind of simulation agnostic. So they included more than just VSIM, but I did the VSIM part of it. And then we tracked the calibration, the differences in headway calibrations to develop, one of the goals of the study was to develop standard recommendations for adjustment factors that you can apply to your Wiedemann behaviors in this case. So if you go out and calibrate your existing study, which is 12 lanes, you say, what happens if we reduce them down to 11? Then we'd be able to recommend an adjustment factor to your Wiedemann parameters. And the different scenarios we looked at specifically on the I-270 corridor, the existing condition was 4 12-foot lanes in the southbound direction. And the 3 builds we looked at were a 5-lane scenario with 12 feet, just to kind of make sure that it wasn't just the extra lane that was improving the facility. And then we had 5 11-foot lanes and 5 10-foot lanes. And then, like I said before, we also were able to generate some recommendations for future use, calibration recommendations and things like that. And I was also able to generate a worksheet that we'll see later on in the presentation, where you can just plug in some data and it spits out and gives you Wiedemann parameters as a starting point for your calibration. All right, so the calibration process. One thing I hate to do when calibrating VSIM is trial and error calibration, because 1, it takes forever, and 2, it sucks. So what I'm going to try and do is, what I tried to do for this project was find a way where we could calibrate our Wiedemann parameters without having to go through the iterative process of checking our data over and over again, then rerunning and doing a little adjustment, and then rerunning and doing a little adjustment. Especially since our model run was about a real-time factor of maybe 10 to 1 on our best case scenario in quick mode. So for a 4-hour run, that wasn't very fun. That was a lot of simulation time. All right, so it all starts with a choice, and this was actually a point that Lucas made out of UGM to me like 3 or 4 years ago. I was asking about, freeways, we use Wiedemann 99, and then urban streets, we use Wiedemann 74, but then what do we do on the weaving areas and ramps? And he said, really, it's more about what are you doing with your speeds. And so quickly, I'm going to it starts with a choice between which one are you going to use on your facility, 74 or 99. And I just kind of put out the equations there so you can kind of see that if you break it down, they more or less have a similar form. It's just one has the velocity square rooted and the other one doesn't. But you see that the B factors kind of do the same thing, and then the coefficient in front of velocity just kind of changes the scaling. All right. Oh, and one little comment I always like to make in my training is, for the vast majority of the parameters in the driver behaviors, I like to think of them as knobs or switches. If you turn the knob up, people generally become more conservative, and if you turn the knobs down, they generally become more aggressive. So that's another way to kind of go about your calibration. All right, so starting with the choice, which one do we choose? And if we overlay the 2 graphs, we can see that one is a square root function and the other one's linear. And the insight that Lucas gave me was, for generally low speeds, you'll want to use Wiedemann 74, and generally high speed, you'll want to use Wiedemann 99. But on a freeway, it just depends on what is your model doing, right? So the I-270 corridor that we were looking at, they were pretty much at breakdown speeds, stop and go traffic the entire time. So I decided to go with Wiedemann 74 because it gives you a nice curve on those low end speeds. But unfortunately, that made my life a lot harder because it's harder to calibrate Wiedemann 74, whereas in Wiedemann 99, you can just kind of create a headway distribution. So again, calibrating Wiedemann 99, you can just collect that raw headway data, and then now you can just create a time distribution and plug it right into CC0 or CC1. So it makes it pretty straightforward to calibrate. But unfortunately, I decided not to use Wiedemann 99 on mine. And plus, it is a good exercise in trying to figure out how to make an efficient way to calibrate your Wiedemann 74 parameters. So we collected the raw data, and then how do we get from the raw speed headway data to average standstill distance, additive part of safety distance, and multiplicative part of safety distance? You can't really go out into the field and say, all right, that's the multiplicative part of the safety distance right there. So we had to somehow take this raw headway data and transform it. And what I found was there was this nice paper done by Hashim Raka and Yu Gao, where they actually did an analysis, and they were able to break down the Wiedemann equations. Again, they did it for multiple different types of simulation software, but specifically for Wiedemann 74. They were able to break it down so that all you needed to input was your steady state free flow speed, your jam density, and your capacity, and it would spit out Wiedemann parameters for you. Okay, and so through their analysis on pages 11 through 14 of their much longer paper, they basically got to a point where what your goal is to do is to take your raw speed headway data and bound it between these two curves. So if you've correctly calibrated the Wiedemann parameters, it should bound your headway data between these two curves. And you can see again the forms that they pulled out of their paper was essentially standstill distance plus a coefficient, and then also and then this upper bound was to add your variance, right? So how much variation do you have? All right, so again, like I said before, if we look at that BX term and the EX term, I'm not going to get into all the math and work through it all, but to give you a brief overview, you can just see that you enter jam density into a few places, you enter your steady state free flow speed into a few places, and your mean saturation flow into a few places, and then it will give you this BX and EX values. All right, once you have this BX and EX, well, now we look again at our Wiedemann parameters. We have the average standstill distance. We have the additive and multiplicative parts of our safety distance. So what do? Well, the additive part of standstill distance is easy to calculate. You take what your jam density is, and you divide 1,000 by your jam density if you're using kilometers, or if you're using miles, then it's 5,280 divided by your jam density, so you get an average, and then subtract out the vehicle length, so you get that average standstill distance from bumper to bumper. Then, for the additive part, you just plug in the BX value that you calculate up there. For the multiplicative part, you do a little transformation, and you do BX times EX minus 1, and that spits out your multiplicative coefficient. And you can just plug those in directly into the driver behaviors. So for my study, that's what I did on all of the different scenarios, and I'll go back to that scenario slide. But then the question becomes less about what parameters are you using and how are you calculating your saturation flow and your jam density and things like that. So you can use things like the pipes model to develop your saturation flow rate and your jam densities. So what I did was, during this project, I put together just an Excel spreadsheet which does the calculations for you, and then I was able to determine what my max free flow speed was, what my saturation flow rate was, and my jam density. And then you can see over here, it will spit out your Wiedemann parameters. So what I did, let me go back. So I gotta go back a few slides to that project overview slide. Should have just made a duplicate, but I didn't think ahead. So if we go back to this, so what I did was, for each one of these conditions here, in this section, I calibrated all the different Wiedemann parameters. And so it made it really easy just to plug in the different outputs from each one of those situations and create Wiedemann parameters for each one. And then what we did as a group was we looked at those individual Wiedemann parameters for the 11-foot, 10-foot, and 12-foot lanes, and we were able to determine an adjustment factor for each one of those lane width drops. Initially, we were going to look at all the combined data, but a funny output was that all the 10-foot data was significantly more aggressive than all the rest, and we found out later that people in Honolulu just seem to tailgate a lot more than people on the mainland. So that was we had to jump some preconception hurdles throughout the course of our study. All right, so again, what I did was I calibrated each one of these. We plugged them into the simulation and we ran it did a normal VISM simulation of a freeway corridor to pull out some outputs. There are some other calibrations that you're going to still want to do. This is just for the following behaviors, so you still got to control your lane change behaviors and things like that. And for those, again, we still had to do a little bit of trial and error to make sure that our queue lengths and things like that were coming out okay, our lane utilization was coming out okay. But what we did was we started with that 12-foot existing conditions and got our lane change behaviors to behave normally. And then as we applied these adjustment factors to our Wiedemann parameters, we were able to see the differences in queuing and things like that. And then going back to my last slide, just kind of going real quick. Faster I get done, the faster we go to break, right? So, all right. So the last thing you'll need to do is you'll need to validate your model. So you could just plug in those Wiedemann parameters, but I wanted to go the extra step where we take you take your VSIM speed and headway data, and you can plot it here on the page 2 of the Excel spreadsheet, and then it will compare it, and it'll plot it between these two curves. So you can see that the shape of, in this case, the shape of these particular settings don't really match the Wiedemann parameters I use, because again, it should fit between those two curves much better. So there might be some adjustment that you might need to do with it. But again, you should always validate your calibrations. Check it against some field data if you can. Now, the benefit of this is now we have a worksheet that I've included in every training set of materials. So whether you take a VSIM intro course or an advanced freeway course, there's this nice little 2-page Excel spreadsheet that all you need to do is plug in a free flow speed and a saturation flow rate and a jam density, and it'll spit out some estimated Wiedemann parameters for you. Now again, this is just a starting point. This isn't necessarily where you want to finish, but it's a good way to cut out 10 or 100 iterations of trial and error on your Wiedemann parameters. And a lot of times you don't have the budget or the time in your study to go out and collect raw speed and headway data, or maybe you're doing it on an urban street where you're using Wiedemann parameters and you're not going to go out and collect necessarily speed and headway data on every little corridor that you do. So what you can do is you can go into like Vistro or Vizoom and pull out capacity or saturation flow rate and input that, and then just use the posted speed limit or the 85th percentile speed as your free flow speed, and then that should be able to spit out some Wiedemann parameters for you to at least get started, so that you can get your calibration, because calibration is always a big hurdle, and hopefully this will make it a little bit easier for you to jump that first hurdle at least. All right, are there any questions for me on my process, on this worksheet? Yeah.
I have a little minor clarification.
Mm-hmm.
When I was working at HW, you actually helped develop the scope for that narrow lane.
Uh-huh.
And originally it was to collect vehicle trajectories.
Mm-hmm.
That's why I did the video.
Mm-hmm.
So FHW is not stupid.
No, I didn't mean to. It was just from my perspective, from what I was specifically doing for this calibration. There were other parts of it, but specifically for my calibration, you could do it with induction loop detector, or you can do it with video detector. It gives you the same results. Yeah. Sorry.
So there's that. I'm just kind of being joking about.
Yeah.
Has PTV ever thought about the calibration process with vehicle trajectories? Individual vehicle trajectories, detailed vehicle trajectories?
That's a good question. That'd be a great question for maybe Lucas or the development team. I'm not sure off the top of my head. I'm not really on the development side. I'm more on just the process side, but we can look in.
What exactly do you mean with that? Well, you will need to do calibration for the location of your project. So you will need real life data there for calibration. So you mean we could add some functionality into Vissim to read in real life data? Okay.
Yeah, I think, with these connected automated vehicles, you may be able to get that data, you're tracking the vehicle at a time resolution and location, so you're getting a lot more detailed information than just at ways and that kind of spot on the road. So I don't know if there's been any thought about difference in the calibration process yet. I know this is kind of futuristic.
Yeah,
People don't have access
but
to that data right now.
well, we think, we hope eventually there will be more of that data, and then we might add something in that direction, I guess. So, but we are in a way already happy if users know that they have to calibrate and do that. And in many cases we just get questions like, can we have the standard parameters for whatever, Singapore, please?
Yeah.
Unfortunately not, because we don't have the data.
Yeah.
And so that is, I think it's a good idea if more of that is available, more of that type of data with detailed vehicle trajectories, to then add something which uses this automatically.
Yeah, I mean, you can get the travel times from GPS when you do your travel time data, or get travel times from other services and stuff like that. And through some spreadsheet magic, you can compare that to some of the time steps and vehicle positioning and stuff like that, if you really wanted to, and that would kind of do the same thing. But yeah, as far as the refined process, it's not there quite yet.
Yeah, and GPS data is not sufficient for gaps, I suppose.
Right, exactly.
That is not good enough.
Okay. Yeah, okay.
Related to the trajectory data calibration, there has been, I think, studies even in the past. We didn't have connected vehicle trajectories, but we had just like a floating car trajectories where I'm sure Brian Park did a bimodal distribution and has shown you can take a vehicle trajectory files from Vissim and create all of these trajectories on segments where you want, and you compare with the field data. That has been done. But one thing that I wanted to ask here, my perspective to this problem would be very different, because HTM says when you want to introduce impact of the lane width, go there and adjust your basic free flow speed. And really, when I drive on a lane which is narrower than 12 feet, I don't care so much about the safety distance. That's not a big difference for me versus 12 or 10 feet. What's the difference is people around me in both lanes next to me. So when HCM makes adjustment, they say go ahead and reduce your base free flow speed by so many miles per hour. And my perspective here would be, I'm not seeing direct connection between those parameters in the Wiedemann models and the final desired speed. And so I would probably change first desired speed, then go into the details.
Yeah.
But then, if you're right, and if you really have to go to the details, I would be wondering to see what's the resulting desired speed for your cars. If you set the desired speed with a range from, let's say, 30 to 35, do you see as a result of the changes in the Wiedemann behavior that it drops down in spite of the fact that you have defined it at a higher level? Because that would be kind of a consequence of what we see in the field.
Yeah. So how we, so part of the process was we took the raw data from the vehicles in these different facilities to generate a speed headway relationship for that particular lane width. And so what we did was we took trajectories and speeds from the entire spectrum from congested all the way up to free flow. So the actual desired speeds going in are kind of independent of this. What this is doing is this is just trying to bound. If you change the free flow speed, I can't do it here. I almost tried to do it, but you can't do it. But if you change the free flow speed, it really just, it'll move this cap up and down. And then the other couple of parameters will adjust the widths. And so what we did was we calibrated to those locations to get the general shape of the curves. And then in the actual model itself for the 10-foot lanes, we actually imposed a 10-mile-an-hour speed reduction on the 10-foot lanes. So the typical desired speed decisions on the existing conditions were 65 miles per hour on the southbound, but the actual speeds during the existing conditions were closer to like 10 to 15. And what we did was when we implemented these parameters, we looked at all the different positions, all those different case scenarios, and we just basically were able to generate an adjustment factor. And so what we did was we started with this I-270, and we calibrated I-270's existing conditions to give us the right speeds both in free flow and congested, as well as queue lengths and lane utilization. So we did all the normal calibrations on that one, and then without using this method. And then when we went to the alternative builds for the lane reductions, that's when we implemented these adjustment factors. Again, I didn't recalibrate specifically for each one. What I did was I took the calibration we took from the existing conditions and then just applied our lane width reduction factor to the Wiedemann parameters, which was somewhere on the order of like 6 to 10% or something like that. So from there, we only really calibrated the existing condition and then just applied this adjustment factor for the other lane widths. And yes, the behaviors could be from the actual width of the lane, and that's what we're expecting. But we do have lateral behaviors in VISM where it can keep track of, if you get too close to each other. But from the scope of this particular project, we were just looking at these adjustment factors for the driver behaviors because we couldn't really go into that granular of detail of saying, okay, why are people necessarily being more cautious? But we just know that the fact is that they are being more cautious, or they do have not necessarily more cautious, but just they do have generally different driver behaviors. And so trying to capture that was our main goal, so that we can make recommendations and things like that. Yeah.
So,
Oh, there are lots of questions, but I will be here during the break too. So, yeah. Yeah, I think we're emailing out everyone's presentations to everybody, so everyone will have a copy. And then if you guys want specifically a copy of this worksheet, I can send that out too.